the dynamic InChI, as subtitle canonical, unique, and on the fly. What does this mean? So here all the numbers, all the names are also listed. So belonging also to the core team is Jonathan Goodman from University of Cambridge. He is also super active in all these InChI committees, because every change of the InChI cannot only be decided by the software developers, but by a complicated substructure of committees, because the InChI is the official molecular identifier from the IUPAC. So there are not several InChIs in parallel. There's only one official InChI, in which we are working on. So what has changed in the InChI? Until 2020, there was one developer or one code specialist. This was Professor Igor Pletnev in Moscow, and unfortunately, he died due to Corona in December 2020. And in his legacy were 3 versions of the code, and that was a little bit complicated because there was not so much documentation. And in the following years, we decided to open up the InChI development to make it more sustainable, to move to GitHub. So every one of you has access to the GitHub and to use it as an open source software under the MIT license. So that it is possible that in-kind contributions from different developers for different branches get possible. As we will see later, the InChI has different kind of branches for different applications. If you think about nano InChI or polymer InChI, and then it is highly useful that more than one person can work on the code. And so again, here the names of the contributors are listed. Yeah, and there's also a web demo, which we can show, I would say, after the official slides. So who wants to test the InChI, wants to get an InChI for his or her molecule, or from the InChI back to a molecule, this can be done by the web demo, which was programmed by Frank Lange, and I'm happy that he could work on this. Okay, going a little bit further, it's really important. The IUPAC, as International Union of Pure and Applied Chemistry, has the initiative of making digital chemistry data fair in a digital way. So fair in the meaning of the FAIR principles. So findable, accessible, interoperable, and reusable. And the InChI has an important role because it connects data, which means if someone is publishing a chemical with the InChI code, another person is publishing biological data or medical activity data, then you can link these data not by any number or IUPAC name. IUPAC names are sometimes complicated, but you have a unique identifier to really link the data afterwards, also between repositories. So there is a controlled governance of the InChI development by the IUPAC and the InChI Trust, so that there are not many changes in the InChI format, so that is in development over decades, not on a short range, but really on a long range. And internally, this organizational collaboration is just made more efficient between IUPAC and InChI Trust because so many news are now coming up. The InChI project in itself exists for more than 20 years. So the InChI Trust in itself has a technical director and works on the development of the InChI and adopts also new developments and has to work on the sustainability. And there are many InChI Trust members, which you see here. So for example, societies, publishers, like for example, RSC or Springer Nature or Wiley, but also important repositories like the CCDC, for example, or the NIST, or also the FDA and other important entities, or all stakeholders in the field which have an interest in maintaining digital standards. And the IUPAC has the scientific oversight and also planning the innovation. And in this, we have the Division 8 and the CPCDS, which is the Committee on Publication and Chemical Data Science. So that's a lot of control. So just to compare with the SMILES world, in the SMILES world, you have multiple dialects of SMILES, and it may be that some repositories are running on dialect A and some on dialect B. In the InChI world, there is one official, actual InChI where everyone has to work with. And so this is a controlled development in the way. And the task of the InChI Trust is also to generate money to maintain the code, but it's also possible to work with in-kind contributions. So if funny inorganic chemists come around the corner and say, hey, we would like to support the InChI like we do in Aachen, then this is also an open model to work on this. So everyone who is interested to contribute to the InChI can give us a mail, and he or she will be integrated quite quickly, I would say. So the project gets you onboarded quite fast. So what are now the news? The latest release is the 1.07.1 in the end of August. And in comparison to the version 1.066 from, I think, 2 years ago, there were a lot of errors and Google Fuzz issues and warnings which need to be removed. And this is George's work to get this out of the code. So the new code does not yet handle inorganic chemistry. This will be on the plan for autumn now. But this brought the code, I would say, from the old model into the new model, so that it is possible to work on the code in this joint collaborative GitLab environment, and not just as a single coder sitting in a single room in this way. So then we are collecting the requirements for the molecular inorganics. The stereochemistry subgroup is working, the tautomers subgroup is working, the S group and S group data works, the isotopology groups. These are all working groups of the InChI, which have been founded many years ago, also supported by IUPAC again, also by IUPAC projects, because there are many requirements coming from the different branches of molecular chemistry. For example, also the Markush InChIs is also an ongoing working group, I think, for more than 10 years now. And there are also prototypes being tested. This is now, for example, on the GitHub of the Goodman lab of Jonathan Goodman, for example. So there are a lot of groups going on in parallel, I would say more than a dozen working groups. And we have now an InChI application framework. So here's again the link to the web demo. Perhaps someone can post this link also in the chat for the others who want to play around a little bit with this. And also the RinChI is one of the application InChIs, is a really active working group, meaning that this is not the core code, but the applied version of the InChI. If you want to describe, for example, reactions, and you say you have A and B gives C and D, then you can use here for the RinChI. And this has also its own GitHub website here. And the MinChI is also an interesting group, which is dealing with mixtures. I think this is also a quite challenging concept and highly needed for chemistry to work on this. And further upcoming news are also in the nano-InChI field, the NinChI field. And sometimes there's also connections between RinChI and MinChI, because we try to describe reactions of mixtures. So this concept is highly useful and adaptable for future applications of the InChI. Going a bit further, we have here the roadmap, but I think I could hand over now to Gerd, because this roadmap is, it has been invented by him.
Yeah, invented. Well, actually, I try to maintain it.
Conceptualized, I would say.
Yeah, conceptualized is the best way, because, you know, dates over here are always a little bit tricky, of course. So basically, you see that we released the InChI 1070 in July, and that was well, actually, it took us quite a while to get the official approval. So that is the basic point over here. Meanwhile, we are with the version .1, and that is released, and we got already some bug reports that have to be immediately fixed. So we are going to have version .2 soon. To come up from one to the other sub versions, we are just using a specific test set of PubChem substance structures. Those are about 300 million. And if the results are identical, we think that the new version can be released as well as the old one. What we are working on right now are the inorganics and organometallics. First part will be described a little bit later into details, meaning that we have to handle different types of representations and make them unique, so that an identifier can be created out of it. And for next year, we're going to have the even more interesting part of stereochemistry of inorganics, including changes in the stereochemistry that we have to add as well. So hopefully we got a prototype at the end of this year for the inorganics, and the prototype in the middle of next year. for the stereochemistry. And you see the other ones are further down the line. Most likely it's not at the end of next year. It may take more time. It really depends how fast we are in getting those official approvals even, because sometimes it may just stop work if we cannot continue. The mentioned application framework, they have come that they are based on standard InChIs. Yeah, so if you think about reaction InChI, it's just describing a reaction using standard InChIs. Same on mixture InChIs and nano InChIs. And the point over here is that we are just working on a common framework for all of them. Main issue is that the number of single characters that are available is limited to 26. And that we have to find ways to get extensions uniquely defined, for example, for reactions and mixture InChIs and nano InChIs. That is some work that is going on right now. It may change perhaps the reaction InChI, that is not clear. Yeah, besides that one, evaluation means, actually nano InChIs are not only an evaluation anymore, they are further down the line. They're going to publish, bring out a new publication about that one very soon. Large molecules, on the other hand, yeah, we are just discussing them once in a while. What we need over there are people that have got more time to work on it. Yeah, that's the roadmap in the current moment. And yeah, let's hope that we come up with that as good and as well as possible. Yeah, so all you need to know about InChI, for those who haven't played with that one, InChI is a unique, is a canonical molecular identifier, meaning it is unique with that one. And that is what you need where whoever is just even coming up with an InChI, it is always just describing the same compound. And vice versa, it's possible as well to have a molecule for each InChI and vice versa, the InChI for each molecule. Yeah, it's a unique identification. The way it's set up, it's interchangeable ordered molecule collections. And what you see over there, that each molecule is described in a certain order, coming with examples later on. And for examples, in terms of the applications, they can be interchanged in certain rules. The rule parts are pretty complex, but at the end, you do not have to take care because it's used in the technical background. Yeah, you see PubChem, reaxis, cost, blah, blah, blah. So databases with altogether at least 1 billion compounds. Or you can do it yourself. You find it in all the major drawing tools or from our site in the web demo that has been built up by Frank. On the next slide, you see an InChI. Nothing in particular. What we tried over here is that you've got a compound, obviously it's a little bit artificial because it's a 35Cl, but we just wanted to describe the different sections of the compound. So the InChI, if you have to read it, the first part is just the version number, so it's a version number 1. Obviously 107, you see where the 1 comes from. Then you've got the chemical formula, and you see there are 2 formula subsets. So you've got the anion and the cation described separately. So the dot is just separating both of them. The second one doesn't, it's just 1 atom, so you do not need a connectivity string. The first one needs one. This is the yellow section. And you see, you just have the numbers, but you do not know anything about the type of bonds that are there. Because that is the major difference between InChI and SMILES or mole files. In the latter two, you have bond descriptions explicitly, while InChI is just giving you connectivity only. Instead, you get all the ligands of each of the atoms. And that's why you need a hydrogen layer. Yeah, so the hydrogen layer is needed to say this atom has got 2 hydrogens, and out of that one, you can recalculate the bonds from the connectivity over to the original bonds, for example, double bond or single bond, because there are other ligands over there. The next one, the green one, is describing the charge. You see in the first, actually, now we have to be careful. You see a semicolon. Semicolon is just referring to the second one. And you see that there is a sodium with a plus sign, and that is represented over here. While the protonation part, which is the next layer, is a P-1 because the acid has got the proton away, and therefore it must be a salt. It's an indirect way to describe the situation over here, but it has been implemented as it is, and with that one, we have to keep it. Stereo is just the standard stereo layer for tetrahedral centers. So T1 is describing the atom. So you see how the numeration starts. So that atom number 1 is that one, the HC on the right side of the acid. And it's got the absolute configuration -1. That's parity, it's better to say, because we do not work with R and S, but internal parity numbers. And the other two, M1, S1, are used to handle mesomeric cases and racemic parts. And what you see is that they may change. Although, for example, the 1- is staying over there, the other two may change, representing another isostereoisotope. Last but not least, the last layer over here is describing the isotope. It's 35Cl. That has to be handled over here, and this is the third atom. With that one, you come up to the isotope layer 0, counting the 35 as the standard masses, and +1, +2, for example, for 37 chlorine. So most of you may know about InChI keys. Those are actually the InChIs that are used most because they are used for web searches, they're used in databases, whatever. And they are just hashed strings combining certain parts of the InChI. You see that formula connectivity hydrogen are just coming up into the first section. In the second section, you got charge protonation and especially stereo and isotopes. And then at the end, you've got SA to describe the version numbering. S means it's a standard InChI over here because we have got a bunch of parameters you can add, and then you just use the standard area. You just have, well, any InChI in that way that you've got settings of a certain parameter. And the very last one is the proton counter, or because what we have, it's no, it must N is neutral. M is +1, O is -1. So it's a +1. Sorry, it's a charge counter within that system. Yeah, how to read an InChI? However, don't do it because it's done via machines, and you've got drawing editor for that one that goes up and down into both of the directions. And the drawing tool is one of them, and we may just show it at the end if not known already. And this is an example how it looks like. Important over here is, for example, this is the new stuff where you've got the different tautomer transformations being available for testing. Unfortunately, it is just hiding another important stuff because within this application, you can, you see it over here. So you see on the middle right part, select InChI version, and that is quite important for us because you can select the current version, which is basically now 0.1, not 0.0 anymore. You can select older version like 106, but you will be able to select the development version as well. Yeah, so that you can already see what we have programmed and test if it makes sense to you or not. Yeah, so
for example, for inorganic chemistry,
especially for inorganic chemistry. And that brings us back to this molecule because that is the stuff we have to work on. Yeah, and now with the next part, just a technical overview, and Nauman, do you want to continue?
Good afternoon, everyone. So actually, about the InChI workflow, coming to this part was not an easy deal because we were dealing with some legacy code which was mostly undocumented and running over thousands and thousands of lines of code and reaching to this point. But now it makes sense and makes our life easier now. So what happens in InChI is that we have input types as mole files and STF. And the starting point starts with the data parsing, which is the input data parsing. And when we have this mole file, we read in the mole file to InChI, and this information from the mole file is then converted into an internal chemical object, which stores obviously in the InChI as InChI is written in C. So it is stored in arrays, and all this information has different structures to it. So suppose properties and other related things to a mole file or a structure are distributed among different types of structures in C, like they are C language-based structures. So they have all this information about internal chemical object, which is not same as the mole file, but also the information is now inside InChI, I would say. And then this internal chemical object is then utilized by steps like normalization and canonicalization. In normalization, basically we have this we take this internal object and then we normalize it depending on what the structure has. Suppose like double bonds, or maybe these bonds are converted to single bonds, and charges are normalized, and the whole processing of normalization takes place here. When after coming from this, we have the canonicalization part, where we allot unique numbers to every atom, and all these unique numbers are then accepted as a canonicalized form of the structure in a molecular graph. And this process of canonicalization is a lengthy process and is a step-by-step process, which forms with the formation of connectivity information. You have all this connectivity information in canonicalization, then you accept the H hydrogen atoms in it. Then after this you can go to like processes like isotopes, stereochemistry also, and then this whole canonicalized form of structure take place. After this we can then convert this canonicalized form into a InChI string, which was already described by Gerd very well, that we have this connectivity part, hydrogen layer part, stereo isotopes depending on the structure. And we have the last step as an optional step, where we can also create a InChI key for it, which helps in finding it on Google or so the InChI key then has these special characters where we can search for a structure or on Google Internet. Then just for the sake of an example, we have this example where just is shown that how data is converted into an internal chemical object from a mole file. Normalization is performed. Then we have this canonicalized numbering, as you can see here, and at the end we have this InChI string as well as the InChI key for the structure. So actually right now we don't have the connection. We suppose a bond to metal is disconnected right now, and due to that we have we suppose the information of connection is lost, and that's why we cannot have inorganics right now. Also, you can see an example for different depictions of ferrocene. You can see that we have multiple depictions of ferrocene, which are by the subcommittee are considered as like these top six depictions are considered as depictions for ferrocene, but not the last two, which will be handled by InChI, but not as ferrocene. So it will not be taken as a ferrocene. So there will be a part where we have this rule set for how it should be drawn. And so because our goal is to not just bring in organics into this, but also that we want the organic part to be still there and not disturbed. So now what we're doing in inorganics, like we want to keep the connectivity and also bring bonds like coordination bonds and haptic bonds. This again, we do not want to alter the C count, H count, or valence count, because in InChI we have the calculation based on valence count. And again, this is the process where we are this whole phenomena on the depiction or the structure is done in normalization, which is a step which is before canonicalization. And yeah, we will be looking into this in organics, that we don't disturb organic part and still can develop on inorganics. So here we can we want to change something in InChI. So up till now we were not drawing hydrogen bonds or hydrogen atoms explicitly, but now we will be, for inorganics, we will be the proposals that we want to draw hydrogen on metal atoms explicitly, except that we don't have to draw hydrogen bonds to organic elements like carbon, nitrogen, or oxygen. But again, the reason behind this is that we don't want to disturb the organic part and yeah, introduce the inorganics also. On the next slide, we have this simple flow chart that we that came from the many discussions from the subcommittee, and here we can see that obviously this is not the, and I would not say that this is the flow that we want to be with, but this is just an idea. We definitely want to bring changes into this also, depending on how new things occur. But still, the starting point is that we have, suppose we will go for a terminal metal atom. We will search for a terminal metal atom in a compound, and based on this, suppose if we found a terminal metal atom, then we have this opportunity to decide on a disconnection table, which has all the values for the difference of electronegativity between the two atoms. Suppose if we found a metal atom, and then we have to look for the neighboring atom, and then we have to calculate pick the value of the difference of electronegativity, and based on that difference we would choose either we have to keep that bond or disconnect. And yeah, this is how the basic idea of flowchart tells us. On the next slide, we can also show the disconnection table itself. So here we see that we have all these different electronegativity values between different atoms, and the red values here you can see is that the ones that should be disconnected, because there is a threshold value that has been set, and if the difference of electronegativity is more than that threshold value, then it should be the bond of the metal should be disconnected, and otherwise we will keep the bond. We also have developed a new table, or I have already made this table into the code itself, because I'm working on the prototype of inorganics and organometallics. So I've already developed this table also, where we have these binary values, yes or no values. Suppose in here you can see 1 or 0. So all those values that are higher than the threshold that are 1, and if we have encountered the value of 1 in the flow chart, or suppose in the structure, then we will disconnect that bond to the metal atom. Otherwise we'll keep it, and this makes it more easier, because now we have to just take a decision of yes or no in the code, and yeah, it will be followed like this. And just take an example of sodium chloride here, NaCl, where we can see that we have got the terminal metal atom has been detected here. So according to values of the electronegativity difference between sodium and chloride, it says that we have to disconnect from the table, and then we have disconnected the bond between the metal and the chloride. So we have this InChI, you can see here. And basically this is what we want to follow right now in terms of our thinking about bringing in organics and organometallics into it. But definitely, as again, we will be changing this flow chart according to new things that we encounter. So that was all for me. I will now make it way for Gerd to shed some light on stereochemistry also.
Now it's getting more interesting in code, because up to now it was pretty straightforward. And the rules we have to use could be developed in an easy way. A few questions about charges in between. Those, I think we can calculate them, but the interesting part for charges is really, where are we able to set them? Yeah. So there are inconsistencies between the way inorganic people think and how InChI works, coming more from the organic side. Yeah, those parts are things we have to develop now, and we have to find out how to best work with it. And the other part that is developed right now is really the stereochemistry of those inorganic compounds. Those two, just as an example, they are nearly identical, except that you've got a single bond on the left and right side on the ethane group and an ethene group on the right one. The right one is square planar, the other one is a tetrahedral one. And it shows that also they are, I think they are not stereoactive because you can just create a mirror plane. How complex it will become to handle those types of molecules. And our work goes, we've got a few ideas all around. Uli has, for example, has developed a system, or Thomas, and that we have to discuss now. How are we going to handle them before we will be able to implement it? Okay, on the next slide, you see the more general stereochemistry. We have to handle, on the top right, you see a classical example of MDL enhanced stereochemistry with and ors, meaning or means you've got one or the other pure center over here, and means it's a racemic center. That have some implications in terms of identity and therefore in terms of the InChI string as well. Below that one, you find a cumulene. Allenes are determined properly, but not cumulines. So we have to extend the number of double bonds we are able to handle. Then you got an atrope isomer. That's the middle case as well, which is a little bit more complicated because you've got a link system over there. On the right side, you've got a standard atrope isomer where you got two ring systems that are hindered because their ligands are too long, so that they interfere to each other, and you've got two versions. And last but not least, but difficult, is the Haworth or Haworth configuration. It's typically used with sugars. You basically think everything that goes up has got an up binding, everything that goes down corresponds to a down bond. The main problem is we are bound to mole files in the current moment, and the mole file doesn't know the block bond in the middle. And with that one, we may have to postpone it. Unless we come up into any good solution how to get it in. And with that one, you see one of the limitations we have with InChI is we need an input format that really transfers our idea. Mole file format is pretty good. We have to become better on these 3 mole files, but that is what we're working on. This is about the applications we have, and the applications mentioned before are primarily reaction InChIs, mixture InChIs, and nano InChIs. They are based on standard InChIs, but are just representing certain workflows. So, for example, mixture InChI, you describe how a mixture is created. Yeah. Thinking about, for example, shampoo. Within a shampoo, you've got multiple mixtures coming into one at the end, and each of them are just created with a certain steering, with a certain temperature, and so on. And we just try to represent that one within this mixture InChI so that you get a unique identifier for those type of mixtures. Nano InChIs have, well, actually, at the end, most likely you can skip the nano and we'll come up to material InChIs. In the nano part, a good example we have to deal with is the titanium dioxide has got 32 different crystal classes. Half of them are toxic, the other half not. Now, obviously, you do not want to brush your teeth with the toxic version. Yeah, and that is the reason why you need identifier for each of those 32 different classes. And what we have over here in terms of implementation is that we get a crystal class identifier along with the InChI. You see, there are new additional properties coming in that makes those materials that are necessary to describe those materials as unique as possible. Our current assumption is that they are coming up to something that is more a class identifier, but let's see how far we're really coming up with that while working on it. And down, you just find a current example of what we have discussed about 1.5 weeks ago. Because what we would like to have is a most common format for all of them. And in the current moment, you have to see that one as a string at the end. We just took it apart because it's easier to understand it. So basically, it's a nanomaterial that consists out of silver and 2 different types of gold. That's why those pop up twice. And the fourth one is just a common solvent, I think, which just all of them are just represented by their standard InChI. And you see with gold to differentiate those ones, additional properties are taken into the game. Then the next line just lets you know how they are linked. So you go from the most inner layer to the outer layers. Yeah? So inner one is gold 2. Then this is surfaced by 1, the silver layer. Then you've got another surface all around, which is 3, the second gold type. And last but not least, you got the organic molecules that are just dotted onto the surface of that. You see, we start to give a description how those materials are set up because all of them just cause different different properties of that material. And the last one is just now I think it's the concentration of each of the layer. But I have to look into that. I'm not, because we are just developing that. I'm not. I do not have everything in my head right now. Okay, on the next slide. Just short summary reaction. InChI has been released in 2017. 1.1 is ready. I just have to test it. It's just a timing issue. 1.2 we are working on. And later on, we are just addressing some other parts of reactions like enzymatic reactions where you cannot, they cannot be represented by a structure anymore. But for example, because you've got a large enzyme, you need a reference to that one. We've set up some rules for that one. We've got some tautomeric restrictions. Yeah, so there are a bunch of details now we are going into, including that we may add information about how a reaction is run, but be aware that those information are only provided as a property, as an auxiliary layer, because they are not part of an identification. Yeah, and I said that we may have a change in the reaction InChI format, depending how the discussion will go. Remaining parts, we have got a QR code proposal that has been published already in 2022. It is not directly linked with InChI, but it is, well, actually it uses InChI. It's a more general part, how to use QR codes in chemistry. The second part, InChI Resolver, is a prototype that does exist for a while. It's important because if you have got an InChI key, you cannot come back to the InChI and the related structure. The InChI key is a one-way endpoint. And if you would like to see that one, you need an InChI Resolver to come back to the original structure. The original idea has been overrun by the fact that we've got large databases now that you can use for that, where you just enter the InChI key and you get the InChI out, like for example, PubChem. Yeah, we talked a little bit about InChI web demo shortly, about the mixture InChI. Yeah, the variable molecules Markush InChI is pretty much in prototyping stage. Once we got consistent examples for that one, we can continue. It's a good question how far we come up. Most likely we're not handling any kind of patterns, but simpler stuff may be used. Large molecules, as I said, it's a little bit in a waiting mode, and nano InChIs I just mentioned already. And with that one, I think we have to thank all of our supporters. And Ballstein Institute, of course, UPAC, that is part of that. We've got NFTI for Chem. I think it's Dahlia, Data Literacy Alliance, Volkswagen Stiftung, doing a lot of funding for us. RWTH Aachen, InChI Trust, all of them.